Topic 3 in environmental chemistry is about acids and bases and how they might harm or benefit the environment. And so let's talk about acids and bases. If we're going to talk about acidic substances and basic substances, we need to be aware of something called the pH scale. And so here's a little picture of some substances if we put them on the pH scale, a scale of 0 all the way up to 14. We're going to come back to this pH scale because I want to talk about how something differs mathematically on the pH scale. Here it is again. As you can see, according to the pH scale, there are substances right at the pH of 7. We call those neutral. Anything lower than 7 we say is acidic, and anything higher than 7 we say is alkaline or basic. Now pH actually stands for the concentration of the hydrogen ion. So the greater the concentration of hydrogen ions in solution, the stronger the acid and the higher the pH. We can identify acids and bases based on properties. So we already know acids have a pH of 0 to almost 7, 7 being neutral. The lower the pH value, the stronger the acid, and we know bases have a pH of above 7 to 14. And the higher the value, the stronger the base. Acids are substances that will break into hydrogen ions when we put them in solution, and bases are substances that would break up into hydroxide. And so if we see the chemical formula of substances, for example, if we see the substance HCl for a chemical formula, aqueous, which means in solution, we can identify that as an acid because the hydrogen ion is at the front here. If we see something that has an OH in it, like sodium hydroxide, NaOH, we can notice that there's this OH at the end, which indicates it's probably a base. Let's talk about characteristics of most acids. So acids in general have a sour taste. Again, be careful. I don't think it's a good idea to taste something that you don't know what it is because it can be very harmful. Acids would turn something called litmus paper red. And we'll work with litmus paper in the lab later on. And lemon juice is an example of an acid. Let's talk about bases. Bases, on the other hand, taste bitter. For example, milk of magnesia. They feel slippery to the touch, like soapy water, and they turn red litmus paper blue. So let's go over a few things. Here's a pH scale, if you can see here, and so if you look at some of the substances, lemon juice, tomato, coffee, milk, what you should notice about these substances is that most food products are acidic and most cleaning products are basic. So that's a general rule of thumb. This is called pH paper, and we dip it into a solution and we match it up then with whatever color it turns to decide how acidic or basic something is. It's much more valuable than litmus paper because we actually get a pH number for it. Let's go back to my first slide, and I want to talk a bit about the pH scale again. Now, pH deals with the hydrogen ion concentration. And so let's look at these numbers here on the left. 10 to the 0, 10 to the negative 1, 10 to the negative 2, and so on. These numbers get smaller and smaller and smaller and smaller as we go this way. And these numbers, with their exponents, mostly negative exponents, stand for the amount of hydrogen ion. Now, when we go from pH 2, which is 10 to the negative 2, to a pH of 3, which is 10 to the negative 3, they differ by a factor of 10. So a pH of 2 is 10 times more concentrated than a pH of 3, and so on. You go down by tens, 10 to the negative 4 or pH 4, 10 to the negative 5 or pH 5. These all differ each level by a factor of 10. So something that's a 1 on the pH scale compared to something that's a 3, pH 3 is 100 times less concentrated or weaker hydrogen ion concentration. Let's look at the brain pop clip quickly now about pH.
Ew. Dear Tim and Moby, how can I find the pH of water? From Jewel So Cool. pH refers to the chemical potential of hydrogen. The pH scale measures how acidic or basic a substance is on a scale of 0 to 14. On the acid side, which measures from 0 to 7 on the pH scale, you can find things like vinegar, lemon juice, battery acid, and the hydrochloric acid in your stomach. On the base, or alkaline side, from 7 to 14, you'll find things like soap, toothpaste, baking soda, and floor cleaner. Really strong acids and bases are found on the ends of the scale, while those near the center of the scale are weaker. Right in the middle, at exactly 7, or pH neutral, you have pure water. Acids contain hydrogen ions, while bases contain hydroxide ions. What are ions? Well, they're just atoms that have either gained or lost electrons. In bases, you'll find hydroxide ions that have gained an electron. The hydrogen ions you find in acids are hydrogen atoms that have had an electron knocked off. These hydrogen ions are always trying to get their electrons back, and they steal electrons from anything handy. That's why when you put something like a metal in acid, the metal starts to dissolve. Bases have the power to neutralize acids. Well, watch what happens when the two combine. The hydroxide ion gives its extra electron to the hydrogen ion. That solves the problem. The hydrogen from the hydrogen ion and the oxygen and hydrogen from the hydroxide ion combine, giving you H2O. And that's water. And water, you remember, is pH neutral. Different kinds of salts are also formed depending on the types of acids and bases involved in the reaction. When Moby poured the baking soda, a base, into the vinegar, an acid, a reaction occurred. The vinegar broke the baking soda into a salt, water, and carbon dioxide. Carbon dioxide was what was in the bubbles. There are also substances called buffers that can block changes in their pH for a period of time. You can find them on buffered aspirin, where they keep your stomach acids from dissolving the medicine too quickly. They're made by combining weak acids and bases. Buffers also occur naturally in the human body, helping our blood keep its pH at or around 7.4. Finding a solution's pH is easy if you have the right tools. Most science labs have a bit of pH litmus paper lying around. These strips are soaked with a chemical indicator, and they turn red when you dip them in an acid. A base will make them turn blue.
I want to stop and talk about this. So let's say you take pH paper and you dip the red paper and it turns red, and you dip the blue and it turns blue. If that happens, you have a neutral substance.
Compare that color to a chart, and you can see how strong that acid or base is. pH is important outside the lab, too. Living things rely on constant pH levels in their environment. If a body of water becomes too acidic, the acids will dissolve metals into the water, and the fish in it will get sick. And if acid rain caused by pollution seeps into a farmer's soil, the crops may not grow. The constant reactions of acids and bases keep our environment from becoming too acidic or too alkaline, which is a good thing for life in general. What did you do? I told you the acid would eat through metal.
Let's finish off by just talking about the environment when it comes to pH. And so the first thing I want to talk about is acid rain. So what happens is sometimes in industries that produce things like nitrous oxides or sulfur dioxides, these chemicals can get into the air, and when they do, they can wash into the rain and come down as rain that's no longer pH 7 but pH of 5, 4, something really low. And if you see my graph down here, in the United States, acid rain became quite a problem in the early 1990s, and you can see the precipitation and the color and pH levels of some parts of the United States. You'll notice that here, where there's heavy population and lots of industry, some bodies of water were at a really critical pH, and they've done a better job of putting devices on things like scrubbers to prevent these pollutions from causing acid rain. This is alkaline lakes. This is not a human-caused problem, but what happens is a lot of limestone that is in lakes can cause the lake to be unnaturally high on the pH scale, and that can be really harmful. When it comes to how deadly does acid rain get, well, anything below pH 4, almost all the fish are going to die in that lake, and so we would consider that pretty deadly. Pool testing is also important. Anyone that has a pool or a hot tub, what happens is they would test the pH, because more or less the disinfectant that you use, which might be chlorine, it doesn't work very well when the pH gets too acidic or too alkaline. And so the chlorine's effectiveness starts to get bad when your pH range is outside of basically this zone. So you want to keep your pH in that zone so your disinfectant, which is chlorine or sometimes bromine, won't work. These are trucks from Australia. If acid rain becomes a problem and your soil is getting too acidic, what you can do is you can counteract that by adding a little bit of base like lime. So these are liming trucks. And that concludes my lesson on understanding the first part of pH. I'll deal with neutralization reactions later.